We welcome the participants once again. We now start with our second session of the day. This session is chaired by Dr. P. Tamilarasan, scientist and assistant professor, Electronics and Electrocatalysis Division, CSIR Central Electrochemical Research Institute, Karaikudi, Tamil Nadu. Dr. P. Tamilarasan has doctorate from Indian Institute of Technology, Madras. He is currently involved in research in the fields of organic electrochemical transistors and in situ spectrochemistry. Also, bioelectrical chemical devices and microbial electrochemical systems. He was awarded with the best PhD thesis in energy applications from IIT Madras in the year 2014. Invention Award from Intellectual Ventures USA. He has published 24 papers in reputed journals, also filed a US patent on hydrocarbon production from carbon dioxide. Today, Sir is here to enhance our knowledge about fuel cells development and its applications. Now, I invite Dr. P. Tamilarasan to take over the session. We welcome you, sir.
Uh, Thank you very much, organizers, for the nice opportunity and a nice introduction as well. I hope I'm audible to you all.
Yes, sir.
Okay, that's great. Okay, and very good morning, everyone. And as I introduced myself, Dr. Tamilarasan from CECRI. Today, in this nice forenoon, I would like to discuss some aspects of fuel cells and its development and applications related topics. So basically, I will touch something related to the fundamentals of fuel cells, related to some thermodynamics and how it works and all, how to fabricate a fuel cell, and what are the different types of fuel cell available, and what are their applications and what advantages, disadvantages, all these things. If you take a fuel cell, what are important components of a fuel cell? For instance, if you take a fuel cell, you have to fuel it. So based on the fuel, you can differentiate whether it is a hydrogen fuel cell or other sources like alcohol fuel cells. And sometimes a catalyst is also important, of course. Mainly platinum is used as a catalyst, but that is not the end. We are actually looking for other catalysts other than platinum because of the limited abundance of platinum. And mainly the fuel cells are named or termed based on their electrolyte. Okay, what kind of electrolyte we have used in that device. Based on that only, the fuel cells are named. And if you wanted to group all these electrolytes, you can group it into two major categories, like cation exchange medium and anion exchange medium. Sometimes you also see in the literature like cation exchange membrane and anion exchange membrane. I am just putting in a broader perspective. So in this whole presentation, I'll touch some of or most of these aspects. Okay, and you can stop me at any point if you wanted to get some clarifications in my presentation. And to start with, where did we start the fuel cell research? If you see the literature, you will definitely come across Sir William. Hello. Sir William Grew, who invented the fuel cell in 1839, almost 180 or almost 190 years back. You can see quite a long legacy of fuel cell development, but not only in 1839, even before people have had that knowledge that from an electrode, from hydrogen or from oxygen, you can produce electricity. His idea is very simple. He knew that if you apply potential to water, it will be splitted into hydrogen and oxygen. And he thought why it is not true in the converse manner. That means why it is not, why it cannot happen in the reverse. That means on an electrode, if you supply hydrogen and oxygen, why don't it produce electricity? So that is the basic idea of Sir Groove. And he actually demonstrated it in 1839. He called it as a gas voltaic battery. Okay, but the same idea was experimented by several other people. He was the first person demonstrated this idea. And from that point, there was a lot of developments, and you will see in the next slide how it has emerged to the current technological status. And we also realized its different applications or different advantages, like it's a non-intermittent source of energy, unlike solar cells or wind energy or ocean energy. In solar cells, you cannot produce electricity in the night. In the wind mills, you cannot produce electricity if there is no wind. But in fuel cells, as long as you supply electricity, you can get energy. Even in batteries, if you are taking a primary battery, they have their own lifetime. If you take secondary batteries or rechargeable batteries, you have to charge them. So those are all intermittent source of energy. But fuel cells are non-intermittent source of energy. As long as you provide fuel and oxidant, you can get energy from the devices. And it is claimed to be a clean source of energy, because at the end of all the chemical reactions, it produces water as a byproduct. So of course, there is an exemption. I'll explain that in the subsequent slides. But in most of the hydrogen, oxygen fuel cells, the byproduct is water. So this is claimed to be a completely clean source of energy. Okay, and here I have just given his experimental device, the Sir Groove's experimental device, where he has demonstrated the production of oxygen and hydrogen. That means water electrolysis using the hydrogen oxygen cell. Okay, so that means whenever you get the oxygen in this tube and hydrogen in this tube, that means there is an electricity supplied to through these wires, and you have connected all these cells in series, so that your potential will be added up. At some point, if you attain the required potential, that means theoretical 1.23 volt, and experimentally it will be more than 1.5 volts. If you supply 1.5 volts to this electrode, then water will be splitted here, and you will get oxygen and hydrogen. So that means these cells are producing electricity. So that is what the experimental demonstration done by Professor Groove. And here is the roadmap of fuel cell development starting from 1839 to the present. You can see development, different stages of development. In 1839, Professor Groove proposed gas voltaic battery, but it was not called as fuel cell at that time. After 50 years, Professor Langer and Mon termed the terminology fuel cell. Okay, they named it as a fuel cell. And it took almost 100 years from Professor Groove's invention to realize a commercializable fuel cell. In 1932, Francis Bacon developed and demonstrated the first alkaline fuel cell, which produced energy density that can be commercialized for some applications. And in 1950s, actually, NASA initially took over the fuel cell research, particularly for their space mission, to supply electrical energy for their space missions. In 1959, Francis Bacon once again, he demonstrated a 5 kilowatt alkaline fuel cell. In 1960s, the Shell started demonstrating the direct methanol fuel cell instead of using hydrogen gas, which has to be stored in high pressure, which needs a lot of care to be handled. They actually took alcohol as a source of hydrogen, and they have demonstrated in 1960s. And in 1970s, phosphoric acid fuel cells have been developed. Those are actually the very initial development of cation exchange fuel cells. If you see the alkaline fuel cells, those are anion exchange fuel cells. You'll understand all these differences in the subsequent slides. And 83 Ballard came into the picture, and now Ballard is one of the major player in fuel cell research and development. And the commercial advancements of all these polymer exchange fuel cell or direct methanol fuel cell or solid oxide fuel cells, all these things have happened in 1990s. So that is where we have concentrated more on development of catalyst and effective utilization of catalysts. So nanotechnology on all these concepts have entered into the picture. And the major breakthrough from my perspective, the major breakthrough is the high feed tube project, which actually demonstrated that a fuel cell can power even a bus. Okay, that is what is the starting, and from that we have seen a lot of development, particularly in the mobility aspects. And not only in the static, if you see the previous demonstrations, all those things, including the 5 kilowatt alkaline fuel cell by Francis Bacon, all these things were demonstrated as static application. Okay, like you can keep it in a room and supply to a complete building. So that is how they have demonstrated. For a mobile application, obviously you should mitigate the liquid phase electrolytes. So you will see in the subsequent slides that has been mitigated in high feed tube project, and they have demonstrated fuel cell powered bus. And in 2007, the polymer electrolyte membrane fuel cell and direct methanol fuel cell have been demonstrated for auxiliary power units. Are you seeing my video? Are you seeing my camera video?
Yes, sir.
If so, I hope you can see a couple of devices I have in my hand. These are some small fuel cells, commercially available fuel cells. This one is a hydrogen fuel cell with an electrode area of 4 square centimeters. And each square centimeter, you will get a current in amperes. So that means you will get at least 4 to 5 ampere current from this device. And this is a direct methanol fuel cell. You can simply put a drop of methanol, and here you have a gas air breathing mode a cathode, so that you can get power with alcohol. Okay, so these are a kind of palm size devices. Okay, very small devices that can produce electricity in amperes. So these kind of developments have happened only in 2007. So that now the fuel cells are found wider applications, like you can use it for charging laptops or batteries or even mobile phones. And you can even carry an alcohol fuel cell for remote locations while you're camping, or while you're going for a trek, or even in remote locations like military borders. There you can actually provide electricity, instantaneous electricity, using these fuel cells. So these kind of auxiliary power units have been commercialized in the first decade of 21st century. And currently there has been a lot of development. Even fuel cells have found educational kits. So you can buy with a couple of thousands of rupees, you can buy a kit of fuel cell, and you can even assemble yourself like a DIY kit, and you can demonstrate to the students. So I just wanted to emphasize that the fuel cell has reached all the way to elementary school. So that is what I wanted to emphasize here. And with this introduction, let's see some thermodynamic aspects. Like if you see, if you take a hydrogen oxygen fuel cell, hydrogen is the fuel and oxygen is the oxidant. Now, if you react these two, you will on this with the support of electrolyte, of course, you will get some usable work, that is W. We will get in terms of electricity, and you will also get heat energy. There will be these reactions are exothermic in nature, so you will get some heat energy. if you reduce the amount of heat generated by some chemical engineering or materials science and engineering, you can convert that energy also into electrical energy. So your electrical output will be higher in terms of potential. Uh, and if you don't manage this heat energy, then it will damage the cell. So heat energy management in fuel cell is a separate big topic. I'm not going to touch much about this topic in the presentation. And finally, it produces water as a byproduct. So that is why it is called as a clean source of energy. And if you see the basic thermodynamic equations, I'm not going to discuss all the deep thermodynamics of fuel cell. Just I'm going to touch some flavors of that. So you have Gibbs free energy, and the self potential in terms of Gibbs free energy. From the enthalpy of the formation of hydrogen molecule and oxygen molecule and water molecule both in liquid phase and gaseous phase. You have different numbers here. These are all the enthalpy of formation of these molecules. Now, from this enthalpy, you can calculate the Gibbs free energy using the entropy changes in these reactions. From this Gibbs free energy, you can calculate the cell potential. And now what you are seeing here is, if you are producing the liquid phase water molecule at the end of the hydrogen oxygen reaction, then you will get a cell potential of 1.23 volt. What happened? So I think the slide is visible now. Hello? Hello?
Sir,
Hello?
it is visible, sir.
Okay, so in between, I didn't know what happened. Okay. And if it is in the vapor form, then you will get 1.18 volt. All these things are theoretical values, but whatever the value you get practically will be much lesser than this, like somewhere close to 1 volt. Okay, and I'll tell you why this 1.23 volt has been dropped into 1 volt in the subsequent slides. Now, if you take a typical fuel cell stack or a typical fuel cell assembly, you have a lot of components here, but the heart of a fuel cell is the membrane electrode assembly called MEA. Okay, the membrane is nothing but your electrolyte. The electrodes are your anode and cathode, and this assembly is the heart of your fuel cell, and it has to be made with a lot of engineering aspects. For instance, if you want to deposit your material or your catalyst on the electrolyte, then you should keep in mind that you should create a porous structure. Why? Because there is something called a three-phase boundary, okay, or triple-phase boundary, where you have your catalyst, your electrolyte, and you also should make a provision to carry the gas, fuel or oxidant all the way to the triple phase boundary. That means at that point, your reactant, your catalyst, and your membrane, all the three should meet. At that point only these reactions happen. Otherwise, whatever the oxygen, whatever the hydrogen you are supplying as a fuel, it will be dissociated on the catalyst surface, and once again it may recombine and it go back to an equilibrium with gaseous hydrogen. You have to harvest the produced proton all the way from the triple phase boundary and transfer all the way through the electrolyte to cathode. Then only you can produce an energy difference, and you will get a potential from a fuel cell. And the second set of components are gas diffusion layers. These are all kind of packings to your electrode that protects your catalyst. And these GDLs should have very good gas permeability into them. Otherwise, there will be some resistance created because of the depletion of depletion of your reactant. And you have gaskets to compensate the height of these GDL and catalyst layers. And here you have the flow cells, flow channels. You supply the reactant, both the fuel and oxygen, through this channel. You generally we make it as a serpentine serpentine nature, so that we enhance the pathway, enhance the path of path length of the gas flow, so that the utilization of gas will be maximum. What happened? All right. Just switch it off. All right. Give me a minute. Sorry. All right. Okay, so other components are like the supporting plate and current collectors. So these things, the current collector is to collect electron and supply all the way through the load to the cathode. Okay. Now, if you build a fuel cell and operate in particular operational condition, you will get a polarization curve something like this. It's a voltage versus current density curve. Now you are seeing different regions here. If you see the ideal performance line, this should be at 1.23 volt. Okay, this point is 1.23 volt. But generally you will not get that much potential. There will be an initial drop in potential to this point. This is because of the fuel crossover losses. What is that? While you are supplying gases to anode and cathode, you will actually supply with certain excess pressure. Excess pressure means instead of one bar or 1 atmospheric pressure outside, you will supply with 1.1 or 1.05 atmosphere. So this leads to a certain amount of fuel crosses over the membrane, or crosses through the membrane all the way to the cathode. What will happen if it crosses? You are supply if it crosses and reaches the cathode, you are actually giving the fuel at cathode as well as at anode. So thermodynamically, these two are at the same potential. So there will be a significant drop in that overall cell potential. So that is what you are seeing here. The potential from 1.23 volt, it will be dropped to a certain point. And we don't know what is that point. It depends on the cell fabrication engineering we have taken. To mitigate this, people used to use thicker electrolytes. While you are using thicker electrolyte, remember your electrolyte conductivity, not conductance, conductivity will be dropped, and obviously you will lose the cell performance. So there should be a very good trade-off between the fuel crossover losses and the electrolyte resistance. Okay. So the next drop will be because of the activation losses. This is because initially your device should take up the fuel and oxidant, and it should ionize, and the ion should ion should cross all the way to either end, maybe from the anode to cathode or cathode to anode. This is important. So these things may not be energetically feasible at the initial stage. So this will consume some amount of energy. So because of that, you will end up with this activation losses, and the ohmic losses are because of the load we are using outside. To draw current, obviously you have to use the load, and while you use a load, you are increasing R value, and you are actually increasing the current. While you're decreasing the load value, you are actually increasing the current. To increase current, you have to decrease load. If you decrease load, V equal to IR. So that is Ohm's law. When the load is dropped, and there will be obviously a trade-off between the current and load, and at the end you will find some drop in potential while you draw more current. And the last portion is the mass transport losses. This is because of the depletion of your fuel. The device may have some limit of producing current because of the supply of your reactant. That leads to the mass transport losses or diffusion losses. And if you see the different type of fuel cells, as I already said, that the fuel cells are grouped based on the electrolyte used in the device. Either it is the anion exchange medium or cation exchange medium. You see the PEM fuel cell, direct methanol fuel cell, and phosphoric acid fuel cell, these are all cation exchange medium fuel cells. And if you see alkaline fuel cell, molten carbonate, and the solid oxide fuel cells, these are all anion exchange fuel cells. Okay. And I'm not going to explain all these reactions. Let's directly go into the different types of fuel cell and some examples of these fuel cells. Let's start with the alkaline fuel cell. This is, as I already said, this is a anion exchange fuel cell where hydrogen is used as a fuel and oxygen is used as an oxidant. And as you know, it is an anion exchange fuel cell, so there should be some anions created in the cathode. There should be some anions produced in the cathode, like hydroxyl anions. And these hydroxyl anions should be transported all the way to the anode. So in that case, you need an electrolyte that is capable of transferring hydroxyl anions. So generally you can use any hydroxides like potassium hydroxide or sodium hydroxide here, particularly in the solution form, so that these hydroxyl anions will be transferred all the way to the anode. At the anode, the catalyst splits hydrogen into a proton and electron. The proton reacts with the hydroxyl anion to produce water, and the electrons all the way goes through the outer circuit, through the load, and it reaches cathode. In the cathode, these electrons will be used once again to produce hydroxyl anions. So this is the overall reaction mechanism here. And if you see the cell operating potential, operating temperature, it will be around 100 to 200 degrees Celsius. And of course, you can also operate at room temperature, but the efficiency will be very less. And you can attain 60 to 70% of efficiency with this cell. And as we have already seen, Professor Bacon demonstrated a 5 kilowatt commercial alkaline fuel cell in 1959. But we have to keep one thing in mind. You are using high concentrated alkaline electrolytes. So these may corrode the cell electrode materials, catalyst, and everything. So we should get a good trade-off between this. Generally, non-precious metal catalysts such as cobalt, nickel, or sometimes silver have been used as a catalyst for these alkaline fuel cells. The major challenge here is the instability of electrolyte. As I already said, it is a high concentrated hydroxide electrolyte. Because of the high pH, the electrolyte and the associated components are unstable. And sometimes the limited conductivity of OH is also playing limiting the performance of the fuel cell. For that, recently, a composite or a polymeric electrolyte was demonstrated, which consists of PAP backbone. That is a polyaryl backbone that actually gives a rigid support so that the chemical stability is good, and it also has hydroxyl anion in its structure, so that you will get the better conductivity. Here they have tested two different electrolytes, one with triphenyl backbone, another one with biphenyl backbone. The triphenyl backbone with 85 composition with NMP was giving the better ionic conductivity. They have used it for fuel cell fuel cell purpose here, and this gives almost 0.9 watt per centimeter square. So that is the maximum power density they got with this fuel cell. And the next one is the molten carbonate fuel cell. Here, of course, the hydrogen is the fuel, but the oxidant is a mixture of oxygen and carbon dioxide. Since it is an anion exchange fuel cell, then obviously you have to produce some anion at the cathode side, and the anion will be transported all the way to the anode side. Here the cation is the carbonate. Here the anion is the carbonate anion produced by carbon dioxide with oxygen. So the carbon dioxide is oxygenated with one oxygen atom, so that it gets 2 minus charge, and this anion is transported to the anode side, where it reacts with the in the presence of catalyst, it reacts with the hydrogen to produce water and carbon dioxide. And since it is using carbon dioxide, we may think that it is not a clean energy, but it is a carbon neutral device. You are taking one carbon dioxide from here, and it is released here. And you can also find out, of course, there is a technology already used in molten carbonate fuel cells, where they separate the carbon dioxide and recirculate here, so that it will be like a closed CO2 cycle. Okay, so in any case, whether you are recirculating or you are just releasing to the atmosphere, this is a carbon neutral technology. So it is claimed to be a clean technology. Since you are using a molten carbonates like sodium bicarbonate, the cell operates at very high temperature, like 650 degrees Celsius, and the attainable efficiency ranges from 40 to 50. Sometimes in the recent reports, even people have reported with 60% efficiency, but that has some other components. So 40 to 50% efficiency can be attained using molten carbonate fuel cells. And there has been, and these are all static fuel cells. So you can produce energy as high as 100 megawatt even using these kind of fuel cells. But these are all not ideal for suitable for portable applications or transportation applications. So you cannot use it to power a bus. Okay. And the latest, very latest advancement of these devices have been like direct carbon fuel cells. I'm not giving a very latest result. It is one of the earlier results. Here, they use carbon as a fuel. Carbon means it's an elemental carbon. You no need to give either in terms of methanol, ethanol. No, it is simply an elemental carbon can be used as a fuel. How it is working? If you see in the cathode side, you are supplying with oxygen, and that oxygen produces oxide anions, and these anions will be transported through the molten electrolyte to the anode. At anode, you are not supplying hydrogen, you are supplying elemental carbon, and this elemental carbon takes these oxygen ions to produce carbon dioxide if it is a 4-electron reaction, or carbon monoxide if it is a 2-electron reactions. And at this point, you would have definitely understood the requirement of suitable catalyst to promote the 4-electron reactions, because carbon dioxide is less harmful compared to carbon monoxide. Carbon monoxide is more harmful, as everyone knows. So this is the basic mechanism in the cell. So this is the cell they have demonstrated for energy production, where they can continuously supply carbon derived from biomass, or even they have demonstrated with the charcoal and other things. But any carbon can be supplied here continuously, and here you have the molten carbonate electrolyte. On the top you have the cathode, and it's an open air cathode, so that you can get oxygen from the atmosphere. Now they used silver mesh as both cathode and anode electrodes, and based on this reaction, they obtained current density as high as, with the closed circuit current density was almost close to 2500 milliampere per centimeter square. That means 2.5 ampere per centimeter square. And the maximum power attained was it was at 800 degrees Celsius. They attained almost 400 milliwatt per centimeter square. Okay. And the long-term stability also they have tested. It was tested up to 90 hours, almost more than 3 days, close to 4 days. And they attained a very good plateau at around 70 milliampere per centimeter square. So this means that it's a kind of a proof of concept. And later there was a lot of development, but this tells us that you no need to simply look for hydrogen. Even you can use elemental carbon as a fuel, and oxygen as a source of energy. Air as a source of oxygen. Okay. And another anion exchange fuel cell is solid oxide fuel cell. Here, if you see the previous two fuel cells, we used liquid phase electrolytes. Those devices have some inherent limitations because of this liquid phase and high temperature operation fuel cells, high temperature operations. Now, this solid state fuel cell, it's a solid oxide fuel cell. Why it is called solid oxide? The electrolyte is the solid oxide. And of course, we can use the electrode also made up of solid oxide, like nickel oxide or some Fe oxides can be used. But the main the important advantage is the liquid. We are mitigating the liquid. You are using electrolyte as a solid phase. Okay, but still it is a high temperature fuel cell. It operates at 1000 degrees Celsius. And generally, we use YSZ, stabilized zirconia. Here, actually, zirconia will be in a cubic phase because of the incorporation of yttria into its matrix. So this YSZ is used as an electrolyte at 1000 degrees Celsius, and even you can use other ceramics like nickel-based some doped oxides can be used. And all these components are solid state. And here once again, hydrogen is used as a fuel and oxygen is used as an oxidant. At the end of the reaction, you will produce water. And here once again, since it is an anion oxygen fuel cell, your oxygen will be transported all the way to anode as an oxygen ion. At anode, it reacts with hydrogen and produces water. And once again, it is a high temperature device. Although it is not using any liquid phase electrolytes, because of its high temperature operation, this is pretty much suitable for static operations like power plants. Okay? And even it has a capability to build a plant with a 100 megawatt capability. And if you see some technological advancement in this device, of course, there have been a lot of electrolytes, catalysts, and a different way of supplying fuels have been developed so far, particularly towards the reduction of the operating temperature. As I already said, it operates at around 1000 degrees Celsius. But if you can reduce the energy, if you can reduce the temperature by 100 or 200 degrees Celsius, you can save a lot of energy, because whatever the energy produced by this fuel cell, a significant portion is once again utilized to maintain this operating temperature. Uh, and in the development of catalysts, the main problem here is you can of course use since it is working with hydrogen fuel and oxygen oxidant. Platinum is the ideal catalyst. Then if you wanted to use platinum, then obviously you have to increase the surface area, so that you will get more electrochemical active surface area. Now if you are making nanoparticles of platinum, the working temperature is 700 to 1000 degrees Celsius. At that high temperature, the platinum nanoparticles migrate and agglomerate together to make bigger particles. Okay, so these things are hindering the stability of the device for long-term operations. So the recent literature gives a demonstration of single atom platinum catalysts. Like they have imbibed single platinum atoms into the Syria matrix, okay, cerium oxide matrix, by using some organic linkers. In this catalyst, the platinum oxygen cerium, the PTOCE, a bond is formed. Because of that, the platinum atoms are highly stable, even at a very high temperature like 700 degrees Celsius. Even for over the 500 hours of operations, these platinum atoms are not migrated and agglomerated. So that kind of stability they have achieved with this catalyst. And here you are seeing the overall device structure. This is this is an SEM image of the device. Here you have the electrolyte and the functional layer. Functional layer is nothing but your catalyst. The PT OCE is the catalyst here. And once again, they have the current collector. All these things are porous in nature, because you will supply gas here, and it should pass all the way through here, and it should reach this three-phase boundary. Okay, the electrolyte, catalyst, and the gas. This three-phase boundary should be created. So you need a very porous catalyst and the current collector layer. Generally, the current collector layers are made up of LSCM. It's a lanthanum, strontium, and chromium doped manganese oxide, which is a well-known high temperature oxide conductor. So if you see here, the circled spots are platinum atoms in Syria matrix. Okay, so effectively they have achieved a single atom catalyst, single atom platinum catalyst, and using this they have obtained a power density as high as 600 milliwatt per centimeter square, and this is almost 10 times higher than the conventional nickel based catalysts. Now, whatever the three different devices we have seen are anion exchange membrane fuel cells, or anion exchange medium based fuel cells. Now we will see a couple of examples of cation exchange medium based fuel cells. In that, the phosphoric acid fuel cell is the very early development of cation exchange medium fuel cell. Here, the phosphoric acid is used as the hydrogen ion conducting medium, because of course the proton has to be transported from anode to cathode, since it is a cation exchange medium. So the hydrogen ions are transported through the phosphoric acid. Okay, and this device works at 150 to 200 degrees Celsius, and it is once again hydrogen oxygen fuel cell. So you will use hydrogen as a fuel at anode, and it will be dissociated into protons and electrons. The protons will pass through all the way through the electrolyte to cathode, and the electron will pass through the outer circuit through the load and reach the cathode. At cathode, the proton, electron will together reduce oxygen into water. And at the end of the reaction, you will get water as a byproduct. Okay, so it is a clean source of energy. And we have started with some liquid phased electrolyte, and we have found that liquid phased electrolyte have some disadvantage. So we end up with a solid oxide fuel cell, which is a solid state electrolyte fuel cell. Now, once again, in the cation exchange fuel cell also, the phosphoric acid fuel cells are liquid phase electrolytes. So obviously they have some operational difficulties. And not only that, these phosphoric acid fuel cells have main disadvantage in terms of the platinum catalyst poisoning. Okay, because of the phosphate anions, the platinum catalysts are poisoned, and this sorry sorry this has been mainly mitigated by preparing platinum based alloys. For instance, in this work they have demonstrated platinum nickel alloy. In this platinum nickel alloy, the PTO bond is weakened, and because of that, the hydroxide to oxygen conversion is effectively hindered. So this leads to the improved efficiency. And okay, sorry. And that is what you are seeing here. If you take a commercial PTC, here you are seeing the peak intensity is very less, and peak is also shifted. The out potential is 84 millivolt. But if you see here, you are seeing the peak is clearly emerged, and the out potential is also reduced to 43 millivolts. And obviously the next example is the proton exchange membrane fuel cells. Here, the operation is quite similar to the phosphoric acid fuel cell, where you will use hydrogen as a fuel, oxygen as an oxidant, and you have the intermediate, in between you have the membrane, and it is a cation exchange membrane, particularly the proton exchange membrane. Okay? And at anode and cathode, both the sides, generally we use platinum as a catalyst, and that is the main advantage as well as disadvantage. The advantage side is platinum is the ideal catalyst, and it has a very good chemical stability, and the use of platinum is also very less. Particularly we use less than 0.25 milligram per centimeter square for cathode, and with the better engineering, you can use 0.05 milligram per centimeter square for the anode. Now, the cation exchange membrane generally used is the Nafion. It is the commercially available sulfonated fluoropolymer developed by DuPont. And so far, there is a lot of research happening on to develop an alternative for this Nafion. But to the best of my knowledge, it was not, of course, there are several reports that have been claimed to be comparable performance, comparable ionic conductivity, comparable stability to Nafion, but those are not commercialized to the level of Nafion so far. Okay, so Nafion is the benchmark electrolyte, and platinum is the benchmark catalyst. And obviously, we are looking for the alternative for both Nafion and platinum catalyst. Okay, and these fuel cells generally operate at very close to room temperature. And if you improve the temperature higher, obviously you will get a better performance. But remember, you are using a polymeric electrolyte, and they may have a stability up to certain temperature. If you're using a Nafion, generally with Nafion 212, we go up to 80 degrees Celsius. Beyond that, it may dehydrate, or the cell may dry up, and gradually your performance will fade out. and generally you will attain an efficiency of 50 to 60%. Still, it is much better than your internal combustion engines, which gives 45, 30 to 40 percent fuel efficiency. And it is a though it is not a completely solid state device, since you are using a polymer membrane, you can sometimes people claim it as a solid state, all solid state device, sometimes claim as a semi solid state device. And its low operating potential and high attainable efficiency really promotes the proton exchange membrane fuel cell as one of the alternative for the conventional energy sources. Now, in the technological advancements, already, as I said, we are looking for better utilization of platinum or no platinum catalysts. That means non-platinum catalysts. So, if you take a better utilization of platinum catalyst, obviously you have to improve the physical surface area to improve the electrochemical active surface area. To improve a physical surface area, generally we make them into nanoparticles. While you break a particle, you're actually increasing the available surface area. Now, there is a correlation between the particle size and electrochemical active surface area reported in 2012. If you decrease the particle size from 3.6 nanometer all the way to 2 nanometers, you're actually seeing the gradual increase in electrochemical active surface area from almost 40 meter square per gram to 70 meter 65 meter square per gram. And so obviously we have to reduce the particle size. That is our main motto. Is it that simple? If you are making smaller particles, they always tend to agglomerate together, because smaller particles agglomerate together to reduce their to overall system energy. Now, if you wanted to retain them as a nanoparticle, you have to anchor or immobilize them on some substrates. What are the ideal substrates for that? Generally, carbon is used for this anchoring purpose because of two or three major reasons. One is its high surface area. If you take a graphene, if you take a single layer graphene, its surface area is 2,700 meters square per gram. And if you take a single wall carbon nanotube, it's half of that, 1,350 meters square per gram. So such a high surface area gives you a lot of scope to immobilize nanoparticles on the surface. Okay, and not only that, these carbon nanostructures have very good electrical conductivity, and you can easily functionalize them using some functional groups like hydroxyl or carboxylic groups. And these functional groups will work as anchoring sites. So these nanoparticles will grow on these, will be anchored on these functional groups. Not only that, these carbon nanostructures have very good chemical and thermal stability also. So putting everything together, when compared to other supporting materials, carbon nanostructures are ideal for uh, ideal as a catalyst support for fuel cell applications. And if you see in the last 2 decades, there is a lot of development in carbon supported platinum nanoparticles. And we have also worked on we have also developed a platinum decorated carbon nanotube, multiple carbon nanotubes, and platinum decorated graphene layers. And you can see here, the platinum nanoparticles are quite fine. Like the average size is around 3 nanometers in both the support. And you can also see they are densely populated. They are not very less in number. They are densely populated, but still they are quite stable on the substrate. Okay. And you may ask, what if you heat the substrates at high temperature? What will happen? That also we have done some research. I will explain in this slide. Uh, as, uh, Actually, reducing the particle size is one way of increasing the utilization of platinum. That means low requirement of platinum. Now, the research is not stopped at low requirement of platinum. They actually wanted to go all the way to no requirement of platinum. Okay. That we will see in the next subsequent slides. In reducing platinum need for particular amount of energy generation. Initially, we saw we'll increase the surface area so that you will increase the electrochemical activity, with a low amount of platinum, you will attain the required energy. Now, instead of course, you can reduce the particle size. How can you utilize platinum much further? Now, there is a possibility like dilution. In platinum catalyst, you can put some non-platinum catalysts, non-platinum atoms like cobalt, nickel, or Fe, ruthenium into the platinum matrix so that the platinum is diluted. If it is diluted, you may ask once again the available platinum surface area will be reduced so that your actual performance also will drop. But for that, there is a solution for that. If you anneal these nanoparticles at certain temperatures such as 700 or 800 degrees Celsius at some reductive atmosphere, what you're seeing here is initially you got some nanoparticle and you have annealed it at 300 degrees Celsius under air atmosphere. Now you are seeing it's PT3CO. In PT3CO, the cobalt, the blue atoms are cobalt in elemental form, and the pink atoms are cobalt in oxide form. So the cobalt is accumulating on the surface and it is oxidized. So this is not a right condition for annealing. So they have moved to annealing at argon atmosphere. Here, once again, we have some cobalt oxide on the top, but generally your surface is enriched with platinum. So that is the important claim here. How to improve it further? This is actually oxide medium. This oxygen medium. Air is an oxygen medium, and argon atmosphere is the inert medium. Why don't we go for some reductive medium, like putting some hydrogen into that medium? Then they have observed substantial accumulation of platinum on the surface, and the cobalt is completely accumulated inside the nanoparticle. So you are seeing the more cobalt density here, but here it is almost 1 to 1. Okay, so in this way, even though you are reducing the platinum utilization by 25%, 25 atomic percent, it is PT3, it's PT3 and CO. So 25 atomic percent you have reduced, but still your surface is enriched with platinum, so it can work as close as platinum catalyst. So you are actually reducing 25% of platinum usage. So this is one way. Another way is you can increase the electrochemical active surface area by annealing the platinum nanoparticles. What will happen if you anneal? We have done an in situ TEM analysis on that. Initially, we have observed when compared to the as synthesized platinum catalyst, the red curve, the green curve, the annealed curve gives a better electrochemical active surface area. That's what you are seeing here. When compared to the red, the green is having more intensity, current density. And we wanted to know what happens to the catalyst and why the electrochemical active surface area is improved. And we have done an in situ TEM analysis. We just focused this particle, and you can see here you are seeing a lattice oriented this direction and lattice oriented this direction. And so that means it is a single particle of almost say in the widthwise it is 2 to 3 nanometer, and in the lengthwise it is almost 5 nanometer, 5 to 6 nanometers. It's a single particle. But while we anneal in situ, we gradually, frame by frame, we have observed what's happening to the particle. It actually turns into a single domain particle. Okay, it has a single crystallite. But if you see here, it has more than two crystallites, one, two, and here you are seeing some amorphous like space. And putting everything together, you have at least 2 to 3 phases of crystals those facets may not be feasible for ORR and hydrogen dissociation reactions. Now, we have annealed and the particle has been recrystallized. And in the broader perspective, we have also observed the relocation or redistribution of nanoparticles. Those have not been agglomerated even at that annealing temperature. And at the end, the advantage here is the improved electrochemical active surface area. Now, there is also another way of improving the utilization of platinum. Like initially here we have taken an alloy nanoparticle and we have annealed it so that you will get a platinum rich surface. Okay, we can do it in different way, like taking a non-platinum metallic substrate, like a metallic nanoparticle, and you can deposit platinum using galvanic displacement on this metallic nanoparticle, so that your core will be a non-platinum metal. Only your shell will be your metallic your platinum surface. If you see this TM image, it is almost the particle size is almost 20 nanometers, but in that your shell thickness is almost 3 to 4 nanometers. If you back calculate, almost 70% of the volume is occupied by your metallic core. Only 30% is occupied by your platinum atoms. So if you see here in the previous technology, in PT3CO, you have reduced the platinum usage, platinum requirement by 25%. But if you see this technology, you can reduce the platinum requirement by 60 to 70%. So with this, you can reduce the requirement of platinum, and per gram of platinum, you can obtain more energy using this technology. And all these discussed technologies are for improving platinum utilization and decreasing requirement of platinum. Now, what about the non-platinum catalyst? We should know we should not use any platinum in the catalyst. Is it possible? There has been a lot of research on this topic for last 3 decades. And mainly the developed catalysts are based on carbon. Okay? Like nitrogen doped carbon or sulfur doped carbon, phosphorus doped carbon. All these things have been tested, but they actually produce a certain energy. They are active in oxygen reduction and hydrogen evolution, of course, but the energy produced by those cells are very less, and the cell potential will also be very less. There alternatively, there are some organometallic compounds or metal organic compounds. In metal organic compounds, particularly the piperidins, okay, or phthalocyanins have been obtained a lot of interest. You can find many research on iron-based phthalocyanins for oxygen reduction reactions. You can see here this iron phthalocyanin gives no oxygen reduction peak while you are using an nitrogen saturated electrolyte. It is a 0.1 molar perchloric acid. While you are while you are saturating it with nitrogen, you will find no oxygen reduction peak. But while you saturate it with oxygen, you are seeing a sharp oxygen reduction peak at around 0.9 volt RHE. And while comparing it with the while comparing it with the commercial catalyst or other PT, of course, it is not compared with the PT, compared with graphene. You are seeing here the black curve. It is iron phthalocyanine. uh, iron thyroxine carbon mixture, and here it is the graphene with iron phthalocyanine. It is a pure iron phthalocyanine. Now, if you compare everything together, you can clearly see the graphene-based system, graphene with iron phthalocyanine gives a much better or activity because of its the graphene's higher conductivity. You can simply compare it with the pure iron phthalocyanine, that is the blue curve somewhere here. The limiting current is around 3 milliampere per centimeter square, but with graphene, it gives almost 5.5 milliampere per centimeter square. Now, the direct alcohol fuel cell is actually a kind of proton exchange membrane fuel cell. There is no difference between the hydrogen fuel cell and direct alcohol fuel cells. Only the difference is your fuel. There we use hydrogen as a fuel. Here we use methanol or ethanol as a fuel, generally alcohol. Okay. Here alcohol is a source of hydrogen. Once again, at anode, the alcohols are dissociated into proton, electron, and carbon dioxide, and carbon dioxide is emitted to the atmosphere. Now here the produced electron and proton goes all the way to cathode and reacts on the catalyst surface to produce water. And by this time you would have known it is emitting carbon dioxide, so it cannot be claimed as a clean source of energy. Okay? And these cells are operating at the similar temperature like 50 to 100 degrees Celsius, and you can attain efficiency. I think I'm wrong here. It would be 40 to 50. It's less than 50% efficiency, and of course it is emitting carbon dioxide. And after seeing all these different types of fuel cells and their working mechanism and recent advancements in that in those different type of fuel cells, now let's see some practical applications where it can be used. For instance, if you see the static fuel cells like solid oxide fuel cell or molten carbonate fuel cell or even alkaline fuel cells, those are all producing very good energy and they are easy to scale up. But the problem is they use extreme conditions like very high temperature or very high pH or liquid state electrolytes. So they cannot be used for transport applications or there is a limitation in using for transport applications. So they can be used for backup power generators, maybe in a building. If you want a backup generator, you can use these kind of fuel cells. These are all good for static applications. But if you want to use it for mobile applications like cars, buses, trains, then obviously we need more safer devices to produce an electrical energy. They have recently several applications have been found, like in transportation, for instance, like short range transportations like warehouse logistics or power clean trucks, forklifts, and so on. All these industrial vehicles, but they actually operate within a boundary. So these are all short range transportations. And recently, long range transportation have also been demonstrated, like fuel cell based cars, fuel cell based truck and trains. You might have seen recently CECRI and NCL Pune together, they have demonstrated a fuel cell powered car. and it came in many media also. And other applications like mobile power generations. Initially, I said we have very small, compact fuel cell devices available commercially. These devices can produce amperes scale current, and in potential ways it will be around 1 volt. So these devices can be used in remote locations like borders and extreme conditions like hill stations. And the power sources for unmanned aerial vehicles like drones also can be used, because in drones battery is used. Batteries are intermittent source of energy sources. So if you wanted to increase the range of these drones, then obviously you can use fuel cells. And boats and submarines. If you can find some recent literatures like in submarines. You can of course submarines are already inside the sea, so you can use ocean energy or ocean thermal energy to produce hydrogen, and those hydrogen can be stored inside the submarine. Whenever you want, you can use these hydrogen to produce electricity using fuel cells. And this technology can be a good alternative to the nuclear power. Nuclear power, obviously, you will use less amount of fuel, and you will get more energy. So that is why a nuclear power is considered for submarines. The same thing you can use with hydrogen also, because you can generate hydrogen inside the ocean itself. So these are all some of the applications I would see in the near future. We will find um, some advantages over other conventional source of energy. And in the advantages side, for instance, if you wanted to generate electricity from fuel, see, there are several stages here. From the chemical energy, you will actually combust it to produce some thermal energy, and this thermal energy is used in turbine to create some mechanical energy, and this mechanical energy is converted into electrical energy using an electric generator. But in fuel cells, it's a direct energy conversion. Directly, chemical energy is converted into electrical energy. So the losses are very less. That is why I said, while you take internal combustion engines, the efficiency is much lesser compared to fuel cells, which is typically around 40 to 70%. And mostly these are all carbon neutral technologies, or clean source of energy, except the direct alcohol fuel cells, where the carbon dioxide is emitted. And if you see the energy density, the specific energy density, hydrogen yields 250 kilojoule per gram, but gasoline yields only 40 kilojoule per gram. So this is almost 6 times higher energy density for hydrogen. So this actually gives a lot of scope, and we have 40 kilojoule per gram, and on top of that, we have only very less efficiency, like 30 or 40% efficiency. On the other hand, you have hydrogen with 6 times higher energy density, or specific energy density, and higher conversion efficiency also. So in that case, compared to the conventional sources like combustion engines, hydrogen energy is much pronounced here, and it also a clean source of energy compared to other sources. And its lifetime, it depends on the type of cell and materials used in it, but when compared to the conventional sources like turbines and electric generators, fuel cells will have higher lifetime because there is no moving part, and they also will produce low noise because there is no moving part. And in the disadvantage side, of course, there is another side of a coin. If you see, currently the technology is quite expensive. This is because with what we are comparing. We are actually comparing with gasoline. Okay, gasoline gives you very less energy density, but still it is more profitable because it is a fossil fuel. We can simply dig it from the earth. But for fuel cells, we have to generate hydrogen. So generation of hydrogen and conversion of hydrogen and everything is costing. Everything costs here, and use of costly platinum catalyst. All these things putting together, the technology is currently costly, but it will be feasible later. uh, it will be feasible later at some point when the gasoline prices are increased. Okay, and we also should uh, note that there is not much infrastructure created for other hydrogen based technologies. Like if you have a car operating with a fuel cell, is it possible to fuel my car anywhere while I'm driving some 100 or 200 kilometers? No, we have fuel stations every few kilometers, but not hydrogen refilling stations. So those are all more important limitation in commercialization of fuel cell based uh, vehicles. Now, we also should admire that the fuel cell based technologies either need hydrogen or to certain extent we can use hydrocarbons like methanol or ethanol. In both the cases, if you are using hydrogen, you have to carry a high pressure hydrogen cylinder in your vehicle. See here they have integrated a hydrogen cylinder, and it is developed by Toyota. And if you see this cylinder will be of several tens of bars hydrogen pressure, and keeping hydrogen with several tens of bar pressure in our car is certainly not that safe. And obviously there are several safety measures have been taken, but still hydrogen cylinders within a traveling car is not safe. So currently research is focusing on low pressure hydrogen storage, like storing hydrogen as hydrates inside a cylinder, and whenever you want you can just release hydrogen, and the hydrates will be back to its metallic form, like a palladium hydride or so on. So these kind of technologies also have been developed, but the overall specific capacity of hydrogen storage is limited. So that is one more bottleneck here. And at the end, handling hydrogen is also very difficult. It's hydrogen is explosive when it is in contact with the air with 4 to 75 volume percent. So high pressure hydrogen in cylinder, and being an explosive in this particular volume percentage concentration. So the safety issues are sounding here. So if we can effectively mitigate all these limitations, then hydrogen related technologies or fuel cell related technologies for transportation will be the uh, good alternative for the current fossil fuel based transportation. And from my perspective, the future prospects of the development will be in R&D side. The fuel cell technologies are expensive now, so obviously we have to reduce the cost. So reducing cost includes production of hydrogen cost, and fabrication of fuel cell costs. All these things have to be reduced. In cell fabrication cost, the main cost is from the noble metals. So if we the current technologies, current research focuses on non-platinum catalyst. If you can find an effective catalyst which is comparable to platinum in terms of efficiency as well as durability, then this will reduce the cost of fuel cell fabrication to large extent. And in the commercialization perspective, uh, if you want to release fuel cell powered electric vehicles, then obviously we need to get a good network of fuel refilling stations. And alternative fuel for hydrogen, obviously hydrogen is as we have seen, hydrogen is a dangerous one. The safety measures are not I mean, we have to take a lot of safety measures to use hydrogen. And the while you are using fuel cell based electric vehicles, the power requirements has to be met. That is one more big limitation. The fuel cells produce some maximum power. You would have seen the polarization curve. In the power curve, we have seen the hook-like structure, hook-like curve. On the top, it is the maximum power from the cell, but that is not sufficient for electric vehicles to operate. So we have to find out, we have to get some hybrid devices like fuel cell with battery or fuel cell with supercapacitor kind of hybrid devices. So this is one more important aspect to be developed for commercialization perspective. In the environmental perspective, the fuel cell technology is claimed to be a greener technology because it emits only water vapor from hydrogen and oxygen. But how the hydrogen is produced, that is very important. If you are using fossil fuels to produce hydrogen and using that hydrogen for fuel cells, you're actually passively emitting carbon dioxide. Okay, so the important thing is you have to get hydrogen from a truly greener, truly renewable source of energy. Okay, like solar cell or wind energy or ocean energy. You use all these renewable source of energies to generate hydrogen. Then it will be truly a greener source of energy. And in the commercialization of solar hydrogen generation is the more feasible way compared to other sources like ocean or geothermal sources. Not only solar hydrogen generation, wind-based hydrogen generation or wind electricity-based hydrogen generation also can be promoted because solar and wind both are intermittent source of energies. So we can store these solar energy and wind energy as in the form of hydrogen, and we can use it whenever we want using a fuel cell. And I'd like to acknowledge a few of them. First of all, CECRI for the opportunity to work some of these results at this institution. And my students, Senapati, Esther, and Jamal Muhammad for their contributions. And my funding agencies, SERB, DST, and one of our industrial partners, Stanvik Forbes, USA. And I would like to thank the organizers, TNAU and ATAL for giving me the opportunity to present my views on fuel cell based technologies to the audience. And thank you very much. If you have any questions, you can ask, and or you can also contact me with my email ID tamilan@secri.res.in. And thank you very much.
Thank you, sir. That was a great session. Now the session is open for discussion. We request the participants to unmute themselves and put forth their queries. We have question in the chat box. On which factors efficiency of fuel cell depends?
The efficiency, of course, it depends on both electrolyte and catalyst. And not only that, for instance, if you are working with a high temperature fuel cell, of course, the temperature matters here. And secondly, uh, all the aspects like design aspects. For instance, in cell fabrication, I have told that the serpentine kind of flow channels. There are several different designs made for the flow channels, gas flow channels. So all these things matters in fuel cell efficiency.
We have a question from Balanaga. What is the percentage of hydrogen fuel usage in India at present?
At present, we of course we can use 100%, but generally we use it with humidified form. But in the commercial vehicles, generally we use with nitrogen, okay, and different compositions we can use. In the oxygen side, starting from air, that means atmospheric air, to pure hydrogen. You can use any composition between. There is something called air breathing mode, so that you can use the atmospheric air to get oxygen from there. Yep. I hope I have answered your question.
Yes, sir. We have another question from Tanuja. For AFC, can we use any other electrolyte than hydroxide?
Um, in fact, we are generating hydroxide ions in the cathode, right? So obviously you need a hydroxide transporting medium. If you are generating something else like a carbonate, but obviously we have a separate topic on molten carbonate fuel cells. But in case, just imagine that you are generating carbonate anions at room temperature. And if you want to use it for alkaline fuel cells, if you want to use for fuel cells, then you can use carbonate solution based electrolytes. But we have to think about the energy feasibilities.